Good day everyone. Today in this short webinar, we will learn about the basic of construction stage analysis and how to perform this in MIDAS Gen. And also I would like to inform you that after this webinar, there will be a short survey that will pop out. So let us start. So these are the main topics of our discussion for today. So we'll tackle about the basic of worldwide application area, the advanced feature, and the GUI of MIDAS Gen. And of course, we will discuss the issues concerning column shortening, the project applications, as well as the demonstration for the construction stage analysis in MIDAS Gen and the other useful features for construction stage analysis. So for the worldwide application area, advanced feature, and the GUI, so MIDAS Gen we call it one-stop solution for building and general structure. So why do we call that? Because we can actually design, analyze, and design our building, plant structures, as well as the spatial structures and the specialty structures. MIDAS Gen also offers you the advanced features. So some of these are the construction stage analysis that we will be doing for today, the post-tension analysis, heat of hydration, and the FEA or the finite element analysis. So for the GUI of MIDAS Gen, if you open the software, this is actually what you can see. So it has this ribbon menu, the toolbars, the task pane, the table windows, status bar. It also has this message window and command line, same with the CAD software that we are familiar with, and the works tree. So this works tree shows the information in our model, like the material properties being assigned, the section, the boundary conditions, and the loadings. So for the issues concerning column shortening. So first, why do we need to perform construction stage analysis? So when we perform the conventional analysis, we assume that all loads are simultaneously applied to a completed structure. That is, when we model our structure, so we assume that the dead load as well as the live load and other loads are being applied simultaneously. But in real construction or in real construction, the initial assumption is not valid since building is constructed in sequence or floor by floor, in which dead load acts sequentially. It may not be even floor by floor, so it can be portion by portion in our floor level. So since construction of a structure is a time-taking process, the material properties, loads, and the boundary conditions may change during this sequence. So in this picture, you can see, so first, in actual construction, we will be having or we will build the lower floor. So after the lower floor, so we can now apply the next floor level. So included with this is the superimposed dead load, like the floor finishes, the self-weight of course, and so on. So this is the real construction or the actual analysis that most of us, or actually all of us engineer should consider. So what are the comparison of the conventional structural analysis and construction stage analysis? So for the conventional structural analysis, so as you can see here, we model our structure as a whole structure and the loads are applied simultaneously. But in construction stage, we actually have different stages of construction. So here we first apply the loadings on the lower floor level. So after we apply the loadings, we can now add the other floor level with its loadings. So there will be a difference in the result if we perform the conventional structural analysis and the construction stage analysis. So what are these? So there will be a difference in forces, especially in the support. So as you can see here in the support, so for the conventional analysis, we can see that the results from in the support is very small, but in construction stage analysis we can see that the reactions or the forces in the support is very large, so this can compensate to a large number or a greater number of rebars. So when we also perform a construction stage analysis or even a conventional analysis, so most of us experience or in our structure we will experience a column shortening. So we have this different column shortening that our structure will experience. So what are these? So first we have this elastic shortening and the inelastic shortening. So for the elastic shortening, it is actually the decrease in the length under the imposed load, which is linearly proportional to the load. So that is when we apply the loading. So in a specific, for example, a column, if we apply a loading into our column directly, so there will be strain that is being, or there will be a decrease in the length that will happen. But for the inelastic shortening, for example, a concrete structure, it will exhibit a creep and shrinkage shortening. So what are these creep and shrinkage? So for the elastic shortening of the concrete structure, since it will experience creep and shrinkage, so first creep. So creep is a time-dependent deformation due to sustained load, and the shrinkage is the decrease in either length or volume of a material due to change in moisture content or chemical changes. So this is actually what happened into our structure. It exhibit, especially in concrete structure, so it exhibit a creep and shrinkage shortening in our column. So basic prerequisite for efficiently predicting the inelastic properties or the creep and shrinkage are the reliable data for the creep and shrinkage properties of the particular concrete mix. And the other one is the analytical procedures for the inclusion of these time effects in the design. So these are the basic prerequisites if we want to predict the creep and shrinkage in our structure. So what are the factors affecting the creep? So first that I can cite is the water cement ratio. So this water cement ratio, when creep increases with every increase in water cement ratio. So creep increases with every increase in water cement ratio. So next is the aggregate properties. So the creep decreases with every increase of the amount of aggregates, and the higher the modulus of elasticity of the aggregates, the lesser the creep it will have. So next that I can cite is the age of concrete. So time plays a big factor in concrete. As time increases, the rate of creep rapidly decreases. The usual time taken by a concrete structure to attain creep is 5 years. So another factor that can affect the creep is the admixture. So some admixture, like the accelerators, are also responsible for causing creep in concrete. The other one is the humidity. Drying condition and humidity of the atmosphere also influence the creep in concrete. So other factors that I can cite is the entrained air, concrete strength, improper curing, and the type of cement. So aside from the factors affecting the creep, there are also factors that affect the shrinkage. So what are these? So again, water cement ratio plays an important role in affecting the creep and shrinkage. So for the shrinkage is greatly influenced by the water-cement ratio. Shrinkage increase as the water-cement ratio increases. The environmental or the drying condition also plays a vital role in the shrinkage. So shrinkage mostly occurs due to the drying condition of the atmosphere. So this shrinkage increases as the humidity decreases. So this environmental condition is also one of the major factors that affect the total volume of shrinkage. So another is the time. Shrinkage also decreases with every increase in time. The next one is again the type of aggregate. So as you can see, the type of aggregate both affects the creep and shrinkage. So the size of aggregate also plays an important factor in shrinkage. As the aggregate increases, the rate of shrinkage decreases. It is also found that concrete made from sandstone shrinks twice than the concrete limestone. Admixture also plays a vital role in affecting the shrinkage. So the presence of calcium chloride increases the shrinkage while lime can reduce this effect. And also other factors are the type of cement, strength of concrete, dimension of elements, and the method of curing. So there are different predictive methods for predicting the creep and shrinkage strains that are currently available in MIDAS Gen. So these are some CEBFIP. We also have this ACI, the PCA, the combined ACI and PCA, and other codes or standards. So in this webinar, we will be using the CEBFIP. So when CEBFIP is selected, so this is how the software actually calculates the strain or the creep and shrinkage in our structure. So the total strain at time t or strain C with a function of t of a concrete member uniaxially loaded at time t naught with a constant stress may be expressed as follows. So this will be the formula in computing the total strain at time t. So this can also be reduced with this formula. So the total strain T with a function of the stress dependent strain and the stress independent strain. So for the creep calculation process based on CEBFIP, so the assumptions and related basic equations for a constant stress applied at time t naught leads to this formula. So this is actually represented by the stress over strain with a function of time. And this portion of the formula is the creep coefficient. So if we perform this, actually thanks to software, we will not be having to perform this, especially if we will be analyzing a high-rise structure. So thanks to software, we will be having these results with this very tedious formula in computing for the creep in our structure. So aside from creep, the shrinkage calculation process based on CEBFIP 2010 is also done here in MIDAS Gen with this formula. So this is actually based from the CEBFIP 2010. So this column shortening affects our structure both for non-structural elements and structural elements. So what are the non-structural elements effect of the column shortening due to the creep and shrinkage also? So some of these are the crack in partition walls, cracks in staircase, so deformation of cladding, mechanical equipment, as well as the architectural finishes. It can also damage the architectural finishes as well as the mechanical equipment and the built-in furnishings. For the structural elements, the effect of column shortening with the combination of creep and shrinkage. Some of these includes the beams could be subjected to higher bending moments as what we have seen a while ago in the comparison of the conventional analysis and the construction stage analysis. There will be also an unbalanced redistribution of loads and the distortion of slabs or beam elements due to differential movements. So some of these, the deformation and breakage of facade, windows, and parapet walls. So this is an example of the effect of column shortening. So it can affect the parapet walls or the windows as well as the facade. There will be also, or we will also experience a reverse in inclination of drainage piping system. Deformation of vertical piping system can also happen into our structure, especially if this column shortening happens. Deformation and breakage of internal partition as well. So those are some of the effects of column shortening into our structure. So some of the movements related to construction sequence also has the pre-slab installation shortening and the post-slab installation shortening. So for the pre-slab installation shortenings, these actually take place up to the time of slab installation. And the post-slab installation shortening takes place after the time of slab installation. So there will be a compensation. So we can actually fix this through leveling. Some of this can be fixed through leveling, but if we experience the post-slab installation shortening, so this will actually damage also the slabs as well and other elements. So for the project application of construction stage analysis in MIDAS Gen, so these are some of the project applications, the notable projects that the construction stage analysis is being applied. So the first one that I can show you is the Burj Khalifa, the gate to the east. So these are some of the notable projects which uses the construction stage analysis as well as MIDAS Gen in their design. The Moscow City Palace Tower and the Shanghai Center Building, including the Guangzhou Twin Tower. Let me go back to the previous slide. So some of the engineers will say that this is being designed using the other software that they are familiar with, but actually when they designed this Burj Khalifa, Midas Gen was used to perform the construction stage analysis. So before in the design process of this structure, Midas Gen is actually a very powerful software, especially in the construction stage analysis. That's why they use Midas Gen here, especially in the stage process or the construction stage process. So for the construction stage analysis in Midas Gen, so this will be the typical floor plan. So we have the 3.77 meters for the base and 5.65, 3.65, and 5.65 distances for the columns. So with a typical floor-to-floor height of 3.2 meters. So this will be the example that we will be going to use. For the schedule of construction, so the basic information that we have here is the three strong floors. So what is these three strong floors? So there will be a 3 levels of shoring. The construction cycle time is 7 days. And the time of removal of lowest level of shores from concreting of top floor is 5 days. So from this figure, as you can see, on the first day, the formwork is being installed. So after third day, the concrete is casted. So the age of concrete here will be 0. On the 8th day, or after 5 days, the second floor installation of formwork is being done. And again, after 2 days, or the 10th day, the concreting of the second floor is being done. So there will be a 1 cycle. So again, after 5 days, in the 15th day, the installation of formwork is being done. And after 2 days, the concrete is casted on the third floor. And after 5 days, the formwork is being done on the fourth floor or being installed. And the removal of formwork is being done on the 22nd day. So what is this actually means? So the age, this 19 days is actually the age of concrete from casting to removal of formwork. So this will be the input in our software. So as you can see in the information, the time of removal of the lowest level of shore from concreting of top floor is 5 days. And there will be 3 levels of shoring and the construction cycle time is 7 days. So after 19 days, there will be a removal, or the age after the age of concrete is 19 days, we will now remove the formwork on the ground floor. So again, after 3 days, the age, or after 2 days, the concrete is being casted, and after 5 days, the installation of formwork is being done, and the removal of formwork on the next floor or the second floor level is being done. So as you can see here, there will be only 3 levels of shoring as based on the information that we have. So in table form, this is actually what we have. So this will be the input that we will do in MIDAS Gen. So what we will be, or what should we notice here is that from the 92nd day, the 11th floor formwork is being removed and the 1 to 3rd floor superimposed dead load is being applied. So it is on the stage 10, and there is actually 3 days of interval, 71, 74, and 77. So same with the 4 to 6 floor, 7 to 9 floor, there is actually a 3 days of interval, and same, the stage duration is 7 days to complete a one whole cycle. So after the 101 days, the structure is being completed. So it is on the stage 12. So the program date or the date of the concrete will be 80 days. And after that, we will now apply the live load in the 112 days. So all in all, for our review, so in every 5 days, the concrete is being casted, and the 2 day is actually for the formwork installation. So a one whole cycle or the construction cycle time, as you can see in the information, is 7 days. So the 5 days is for the concrete casting and the 2 days allotted is for the formwork installation. And again, there is three strong floors that we should consider here. So to apply this in MIDAS Gen, so first thing that we should do is go to the Properties tab, and we can define first the creep and shrinkage. So here we will be defining first the creep and shrinkage in our materials or the time dependent material. So we can add. So first here that I can add is for the frame. So let me name it as frame. So I will add two time dependent material for the frame and the walls. So I will be choosing CEB FIP 2010 and the concrete compressive strength. So this concrete compressive strength is based on the material that we actually assigned. So let us review first. Let me go first on the works tree. So this is the properties. So based on the tree menu, we will see the properties of our structure or the information. So for the information, we have defined the two materials. For the frame, so let us see. For the frame, we have the grade C5000, and for the walls, we also have the grade C5000. So we have three sections. So for the columns, the girder, exterior girder, and the interior girders. So the thickness of our shear wall will be 0.3, and we have a support of fixed condition. So I will not discuss more on the modeling. And we also have the different load case like the superimposed dead load and the self weight of our structure. And of course the live load. So we have approximately 13 number of floors. So this is actually good here in MIDAS Gen because in the tree menu you will see the lots of information in your model. So again, let us start with the construction stage analysis. So first thing that we should do is apply the time dependent material, the creep and shrinkage. So I can now again click on apply, and I will define two time dependent material, one for the frame using CAB FIP 2010, and the concrete compressive strength, so 5000 psi or approximately 34.5 kilonewton per meter squared. So you will have to also input the relative humidity of ambient environment. So let us use here in our example the default 70% and the notional size of member. So this notional size of member is based on the sizes or the sectional area of our frame. So what is good here in MIDAS Gen, so if we are performing or we are actually computing for the notional size of our frame members, so there is actually an what do you call this, there is actually auto calculation of notional members for frame structure. So you will have just to do this in the change property command. So for the frame structure, I can just input any number here, let's say 1, because what I will do later is to actually compute or the auto calculation of notional member based on MIDAS. So you will also have to select the type of cement in your structure. So I can now click on apply, and I can also add for the walls. So for the walls, I can input the name of the time dependent material as wall using again code CEBFIP 2010, same material and or properties. And for the notional size of member, so since Midas Gen only compute for the notional size of member of the frame elements, so here in Midas Gen, we can also compute manually the notional size of member for the wall elements. So how do we compute this? We have this formula 2 area of concrete over U. So the U is the perimeter in contact with atmosphere. So this perimeter is actually twice the length, and the section area is length times thickness. So if we do this formula, it will come out or similarly or approximately near the section thickness of our wall. So for simplicity in our design, I will just use the thickness of our wall, which is 0.3. And we can now also show the results. So for the result, you can see the creep function data. So the creep coefficient versus the time. We can also view the shrinkage. So start of loading, end of loading is where the creep coefficient, for example, the creep coefficient will be applied, and it will not be applied after the end of loading. So number of steps, we can actually increase the number of steps to generate a larger graph, and you can also save this graph by clicking this button. So I can just close this and click on OK. So the time dependent material, the creep and shrinkage is now being defined. So I can now click close. So the next thing that we should do is to apply the time dependent compressive strength. So I can now add the time dependent compressive strength. Again, I can just name it as compressive, for example. And for the development of strength, I can use the same model or procedure using the CEB FIP 2010, and the mean compressive strength of concrete at the age of 28 days. So for example, this is the FCK. So the FCK that we use in our structure is the 5000 psi or the 34.5 plus the delta F. So what is this delta F? Based on CEB FIP 2010, we can use the 8 megapascal as delta F if we do not have an actual test that is being performed, or if we have a delta, or if we conducted a test, so we can add the actual delta F in our mean compressive strength. So since we do not have an actual test, I can just use 8 megapascal. So for the type of cement, so I can select the different type of cement based on the material that is being given. So we can just redraw the graph, and again we can save this graph by clicking this button. So I can now click on OK. So for the change property, this is where we actually auto calculate the notional size of the member. So for the notional size of the member, I can just select the whole structure. So this is for the frame elements that we have defined first in the creep and shrinkage time dependent material. So after selecting all the structure, I can now click on apply. By clicking this button, we will now see the notional size of the member that is being calculated by the program. So actually this can be applied only on the frame structure. So after we apply after we get the notional size of the member, so what we should do next is to link the linear material properties with the time dependent properties using this material link. So I can just select first the frame element. So let us check first again. Let us check first for the CEB FIP. We have defined the CEB for the frame or the time dependent for the frame as well as the compressive strength. So I just check if we actually applied or if we actually defined the time dependent material. So again, I can just go to the material link. For the creep and shrinkage, I can just select the frame for the frame element, and for the compressive strength, the one that we have defined, and I can link the frame properties or the linear material properties here. And for the walls, same process. So the linking of the linear material properties with the time dependent properties is now being done. So again, let us check if it is now in black. So before it is blue, so meaning it is not being applied yet. So after we have linked this, so it is now being applied into the structure. So after the material link or the time dependent material properties, what we should do next is to go to the load tab. So from the load tab, we will now go to the construction stage. So here we can define the different construction stage in our structure. We can define the different construction stage. We can also activate or deactivate certain function in our model. But what is great here in MIDAS Gen is you can actually use the construction stage wizard. So it has a construction stage wizard for easily modeling or easily assigning the construction stage. So what I can do here is to click the automatic generation. So for the automatic generation for the construction stage, I can first select the self-weight of our structure and the story increment. So what is this story increment? So this is the number of the story we want to generate the construction stage. So for this example, I will use 1. So I will generate a different construction stage at every floor level. So what is this stage duration? So this stage duration is the cycle of the construction. So let me go back to the presentation. So it is the construction cycle time. So this is actually the concreting as well as the installation of formworks. So it is 7 days. So we will input the stage duration of 7 days and the member age. So what is this member age? So this age is the age of concrete from casting to removal of formwork. So based on our diagram or based on our image, so the age of concrete where the formwork is being removed is 19 days. So that is what the member age is all about. The age of concrete from casting to removal of formwork. So 19 days. So aside from self-weight, we can also add, of course, the superimposed dead load. So for the superimposed dead load from the table, now from the table, here the superimposed dead load, there is a difference of 3 days. 71 to 74, 74 to 77, the application of superimposed dead load. So here, I will apply the story increment of 3 days. So why 3 days? So 3 days because 1 to 3rd floor, 4 to 6th floor, 7 to 9th floor, and the last is the 12th floor. I mean the 10 to 12th floor, and of course the last one. So the starting day is we can start at 71 days. So these 71 days can be found here also, the application of the superimposed dead load. So starting at the 71st day, we will apply the superimposed dead load. And the day increment, as I have previously said before, it is 3 days. So again, why 3 days? So these 3 days, so 71 to 74, 74 to 77, and so on. So aside from the superimposed dead load, we can also add for the live load. So I can also select for the live load and the story increment. So after the 12 level. So the starting day here is the last day, which is the 112 days where the live load is being applied. And the day increment, I can just use one value. So for simplicity, or for the application of live load, so it will take just 1 day to apply. Let's say, for example. So I can now click on OK, and the erection sequence list is now being generated, or the construction stage is now being generated. So after this, I can now click on OK. So after we apply the construction stage wizard, so again, let us review. We apply the superimposed dead load starting at 71st day. So at the 112th day, we can now apply the live loads. So we also have to review that after we have applied the change of property or the calculation of the notional size, we'll also apply the link properties. So this process is actually what we should follow, especially when we are performing a construction stage analysis. So the different stages is being applied, or for the construction stage. And the last one is we can now check for the construction stage that is being generated. So this is the construction stage that is being generated. So construction stage 1. So the first floor, second floor is being generated, the third floor, fifth floor, 11th floor, and the dummy is actually when we apply the live load also in our structure. What if we want to apply, or we want to include the after 3 years, we want to see the column shortening after 3 years. So we can also add, using the define construction stage, we can also add, for example, 3 years. We want to investigate our structure after 3 years, what will be the effect of column shortening. So for the 3 years, so it will have 3 years. Let's say we have 365 a year. So we will have 10,000 or 1,095 days. So we will not be activating or deactivate certain part of our structure. So I can now click on OK. So the 3 years is now being applied, or we will investigate it here in MIDAS Gen after 3 years. So what will be the effect of column shortening after 3 years also? So aside from defining other construction stage, we can now go on to the analysis tab. In the analysis tab, we can select the construction stage since we are performing a construction stage. And for the final stage, we can select, for example, other stages if we want to investigate a construction stage up to this stage of our structure. So if we are going to use last stage, so we will investigate for the whole structure. So the analysis type that we can use here is linear analysis. If we have a tension only or compression only material in our structure, we can also apply the nonlinear analysis. So of course, we will include the time-dependent properties. So let us check for the time-dependent uh, effect control. So for the type, if we want to consider only the creep, the shrinkage only, and if we want to consider both creep and shrinkage, so we can just select creep and shrinkage, and we can modify the different iterations or tolerances into our structure. So for the load case to be distinguished from dead load for construction stage output. So since we are performing a construction stage analysis, so the self-weight as well as the superimposed dead load is being generated, including also the live load in our construction stage analysis. But if we want to separately check for the live load effect, so we can just select the live load and click on add. So I can now click on OK, and we can now perform the analysis. So what you have seen is that here in MIDAS Gen, we have seen the construction stage wizard. So this construction stage wizard is actually a very useful and a powerful feature in MIDAS Gen, where you can actually see or where you can actually apply the different stages into your structure without doing the manual calculation. So let us open a recently performed analysis file. So this is just the same file. So I just performed the analysis here. So after running the analysis, we can also check the result. So for the result, so let us select first the construction stage load. So for example, I can just check for the construction stage 3 or construction stage level 3, and I can just check the results. So for example, the reaction forces and moment. So let us check only the Z or the axial. Let us check also for the values. So as you can see, for example here, the values for the reaction is 311.8. So as we increase the number of level, of course, the reaction also increases. And if we want to consider after we have applied all the loadings, so you can see here the reactions at different stages of construction. So aside from checking for the reaction, we can also check for the beam diagrams. So for the beam diagrams, let's say I can just select first for the construction stage 3, click on apply. So this will be the reaction or the forces or the moments which actually apply into our structure on the construction stage level 3. And as we increase the number of floor, of course, the reaction or the moment also increases. So after 3 years, as you can see, it will require a greater number of rebar or a greater number of section if actually it fails in section properties or rebar properties. So in the dummy, we can in the dummy level construction stage dummy, we actually applied all the loadings including the live load. So it requires 51.4. So after 3 years, as you can see, it reduces. For the construction stage level 10, only requires a minimum number of rebars, but as the construction stage progress, it requires larger number of rebars. So what I am referring is the moments which can be equal into rebars if we calculate it. So after we have checked the reaction or the forces that acts into our structure at different stage of construction, we can now also view the column shortening. So for the column shortening, so we can just add the different column data that we want to view. For example, the creep plus up to casting. So meaning it is the pre-slab construction where the slab is not being installed yet or the before slab. So for the creep plus sub to casting, so subsequent slab is being done here or the post slab is being installed. So up to casting. So that means the plus slab to casting included the slab. For the up to casting, the slab is not yet included. So here in our example, I just select the creep plus sub, elastic plus sub, and the shrinkage plus sub, and the total plus sub. So again, plus sub, so meaning subsequent slab, the slab is being casted. So up to slab. If it is up to slab, again, up to casting, so meaning the slab is not being applied yet. For example, so checking this or selecting this column data, so we can now view the construction stage. So let us see for after applying the, for example, after completing the structure and applying the dead load, so we can just check. So here, shrinkage itself does not affect much on the displacement. in the structure as well as the creep itself. So this is the elastic deformation, and the combined of the creep and shrinkage as well as the elastic will have this deformation. So as you can see, it will exhibit a large deformation into the structure. So after 3 years, so let us view the construction stage after 3 years. So I just changed the unit to millimeter. So after 3 years, so this is what happened. There is a very large displacement considering the creep, shrinkage, and the elastic deformation. So aside from viewing the graph, you can also save the graph as Excel file. Construction stage. So this is the graph that is being generated. The information on the graph is now being reflected if we save it in Excel file. So here we can investigate how much how our structure behave as per construction level. So we will exhibit the different displacement considering the time dependency of our material, which is the creep and shrinkage into our structure. And as you can see, to wrap this up, is as you can see is that the elastic shortening as well as the creep and shrinkage included will have the most displacement into our structure. So approximately it shows that the maximum is 36.6 millimeters at 12th floor. So let us check again for last for separate construction level. So as you can see, here is the graph which shows for the construction level 5 or construction stage 5, it will have a maximum displacement of 1.42 at 4th floor. So stage by stage, we can check how much the displacement will happen into our structure. So in this case, we can prevent any other failure if possible if we can check especially the displacement that will actually occurs when we are in the construction process. So aside from performing the construction stage analysis here in MIDAS, so this is actually the summary of the process. So first is that we define the materials and section, assign the elements, the boundaries and loads to the groups, define the time-dependent materials like the creep and shrinkage as well as the compressive strength. We can also now, after that, enter the construction stage analysis data, the duration of the construction stage. We can activate or deactivate element, boundary, or load groups. So what we have performed is that we use the construction stage wizard in the example. So after we have entered the different construction stage analysis data, we can now perform the analysis, check for the results for each stage of construction, and check for the column shortening. So the last part will be the other useful features for construction stage analysis. So here in MIDAS Gen, what we have performed is using the construction stage wizard. So this wizard allow us to define the timing of elements created and loadings applied to the construction stage during the erection of the building. So it will be easily for us to assign the different construction stage using this construction stage wizard that you have saw in our demonstration. So construction stage analysis for composite members are also available here in MIDAS Gen. So as you can see, we can define an analytical model for each construction stage by assigning or activating and inactivating the section corresponds to each construction stage of a composite building. By using a composite section for construction stage, we can consider the construction sequence with creep and shrinkage effect also. And the material stiffness changes for crack section. So section stiffness scale factors can be included in the boundary groups for construction stage analysis. So the scale factors are also applied to composite sections for construction stages. The spring supports for soil structure or the SSI. So here, springs can be activated or deactivated during construction stage analysis. And the last one, if we are designing a structure having a pre-stress load, so pre-stress load can be considered also in construction stage analysis. The tendon, primary, secondary forces are provided with pre-stress loss graph. So that will be all. So as you can see again, different advanced features are available if we are doing construction stage. The first one is the construction stage wizard. The second is for the composite members. We can apply the construction stage. The material stiffness can also be included in the construction stage process. The spring supports or the SSI or the soil spring supports for soil interaction can also be considered by activating or deactivating this in construction stage analysis. And the last one is the tendon loss that I have here is we can consider the pre-stress beam load or pre-stress load we can consider in construction stage analysis. So if you have further questions or concerns, don't hesitate to contact us at philippines@midasit.com or phinquiry@midasit.com. So that will be all. Thank you very much.